Alrighty. Well, it is at the top of the hour, so we can go ahead. And thank you, Remy, for continuing to admit folks from the waiting room. Welcome to the American Solar Energy Society's Resource Application webinar. We're so happy you can join us today. My name is Ella Nielsen, and I am the Programs Director here at ASES. To kick off, I would like to inform you of who the American Solar Energy Society is and highlight some of our current events and programs. The American Solar Energy Society is a 501c3 nonprofit that was established in 1954. So just last year, we celebrated our 70th anniversary. We advocate for sustainable living and 100% renewable energy by sharing information, events, and resources to cultivate community and power progress. You are welcome to join our community at any time at ases.org/join. And you all are special. We can give you a webinar discount because you're all here, and it's just code webinar at checkout on ases.org/join. Or if you're already a member and want to renew for 10% off, it's just ases.org/renew. Moving on, wanted to share a quick update. So in partnership with Twende Solar, we are so proud to be hosting the ASES Women's Hands-on PV Workshop. It's taking place in just a couple of weeks on July 28th through August 1st. It's from 8 a.m. to 5 p.m., all in Boulder, Colorado. We're excited to have Marlene Brown, who is a longtime ASES supporter and ASES Life member, join us as our PV workshop instructor. There is no experience needed, and we welcome all women identifying folks to join in just a couple weeks. There's still time to register for our 54th Annual National Solar Conference, Solar 2025. Our theme this year is Innovation for Universal Renewable Energy Access. The conference will be a completely net zero emissions event and will be held in Boulder, Colorado at the University of Colorado Boulder. And that will be taking place on August 4th through 6th, so just in less than a month. You're welcome to head over to ases.org/conference to register, view the conference schedule, and check out all of our amazing lineup of speakers, etc. The 30th Annual National Solar Tour Showcase Weekend will be taking place on October 3rd through 5th. We'll be celebrating our 30th anniversary, and it'll feature tours with solar and sustainable technologies all across the US and all 50 states. Signups are open, and you are welcome to host a tour site or a local tour. So be sure to sign up and get your tour on the map at nationalsolartour.org. We're excited to share that our Solar Today magazine summer issue, it just came out. It's all about agrivoltaics and harnessing solar power in agriculture to revitalize rural economies. So you're welcome to check out some of the public articles on ases.org/solartoday, or you're welcome to subscribe to receive the digital and printed version on ases.org/join. Thank you so much. We appreciate you listening to these quick ASES updates. I do want to note that this webinar will be available in a recorded format soon on YouTube. I'll follow up with everyone once it's available. I will ask that you submit your comments to the chat section throughout the presentation, and Remy will be kind of moderating that. But we would like to see all of your great questions all throughout the webinar, and we'll do our best to review everything at the end of the presentation. So without further ado, I will hand it off to Remy Akinwami. He is our Vice Chair of the Resource Applications Division. And yeah, we're excited to have you introduce our speaker, Remy. Thank you so much.
Yeah, thanks, Ella. Thanks for the introduction. And hello, everybody. My name is Remy Akinwami. I'm a PhD student at Colorado School of Mines and also a graduate researcher at the National Renewable Energy Lab in Golden. And yeah, just as Ella introduced, I'm the Vice Chair of the Resource Applications Division here at ASES, and I'm supporting Manojit Sengupta, who is the chair of the division and also a senior scientist here at NRO. And yeah, if this is your first time joining one of our events or webinars, or you've been with ASIS prior to now, I'm really excited that you're here. We're glad you're here. And today's topic is both timely, I think, and it's important for everyone, anyone working in or curious about solar and renewable energy forecasting, basically. So just a quick background on the resource applications divisions. I would say the RA division focuses on how we gather data, how we model and apply solar resource data to support everything from siting to system design and grid operations, and as well market participation. And as solar scales, resource applications are central to ensuring that reliability and performance in energy systems. We also have the other divisions within the ASES community that includes there's the PV division that's chaired by Rich Stromberg. Energy economics, I think Waldon also in the audience is the chair of the division. There's solar thermal, if you're interested in conversion from solar to thermal. There's policy division, solar buildings. The list grows basically. If you're interested in joining any of these divisions as well, you can just do that by signing up on the community website in the ACES webpage. We welcome everybody. That includes students, researchers, professionals. Doesn't really matter what you do as long as you're really interested in solar energy or renewable energy or in the energy transition, basically. Just you're all welcome. And yeah, this is the first webinar we've had at the Resource Applications Division since November 2021, I think. Yeah. And back then, the session was led by James Stalker, who was serving as the chair, who was serving as chair of the division at that time. And he spoke on accelerating global solar adoption through some cutting edge science. You can still actually you can find the talk on the ACES archives, webinar archives on YouTube, which also this presentation will be there as well. But a lot has changed since then. Solar has continued to expand rapidly. It's continued to grow both in the US and globally. And at this stage, I think the focus of our division is shifting from just not just growth, but to sustain and reliable operations. And that shift is essential because, to continue to make the case for solar and renewable energy, we need to sort of ensure that these systems can deliver reliable, secure power when we need it. So I believe forecasting plays a big role in that, and that's what makes today's discussion very relevant. So with that, I will try to introduce our featured presenter. Uh, our presenter is going to be Muhy Eddin Za'ter, and Muhy is a colleague of mine and a researcher in power systems operations and forecasting at the University of Colorado Boulder. His work explores how machine learning can help solve real-world challenges in grid reliability and improve forecasting in energy systems. So in today's talk, we will walk us through the evolution of forecasting in power systems. We will talk about the current role of machine learning and how these foundation models may be the future of solar forecasting. Yeah, so like Ella said, we'll have time for question and answers after the end of the talk. So feel free to drop your questions in the Q&A chat box, and I'll be monitoring that. And then with that, I will just hand it over to Muhy to share his screen and begin his presentation. And thank you for being here today, Muhy.
Thank you for the introduction, and thank you everyone for organizing this webinar, and thank you everyone for attending and signing up. And I'm happy to be here. I just want to make sure if my voice is clear. Sounds good. So welcome today, and at the heart of resource allocation in general lies one of the topics of forecasting, which has a lot of forecasting alone could mean a lot of things. But in this context, we're talking about time series forecasting and more specifically about solar forecasting for power system applications. So what we'll talk about today as a table of contents is why do we need forecasting to start with, and a brief introduction on forecasting, what's its attributes, and how actually important forecasting is. So and then we're gonna dig a little more deeper about the algorithms for solar forecasting, what people used to use, what are their limitations, and why do we need to explore new ones, and why machine learning in general and foundation models, and more specifically, is a good solution for that, and why now is a good time to use this solution. And we're going to talk more about the transformer architecture of which is one of the popular architecture in machine learning, and talking about what it can do to this field and more specifically. So to start with, why would we need forecasting in power systems? So the main goal of forecasting in power systems, either it's load forecasting, wind forecasting, or whatever time series forecasting, is mainly to minimize uncertainty. And uncertainty cannot be completely eliminated, but the better that we minimize this uncertainty, the more cost effective our solution would be, the more we would be able to adequately plan for everything. So minimizing uncertainty is the main reason for forecasting. And which begs the question, what are the main resources or the main sources of uncertainty in power systems? Well, the sources of uncertainty in power systems are kind of endless. There's a lot of uncertainties. For example, we have no idea about what would be the natural gas price would be in like 5 years. We have no idea about also what would the load look like in 10 years. We also don't know the exact profile of the load tomorrow. So basically, and generally, there are mainly two types of uncertainties in power systems if we categorize them based on their periods. So, for example, at first you have the long term and the long term uncertainties, which, as we said, we kind of see all of these studies and projections, and also which makes it to the news headlines that, for example, right now we can hear a lot about data centers are going or artificial intelligence based data centers or computation based data centers are going to increase the capacity the energy consumption of the US by almost 12%, or you can hear a lot about of these uncertainties, as well as the long-term one, which what would be the natural gas prices be next year at least. And we know that, and why are also these difficult and important to forecast? Because a lot of things might come into account that affect these. For example, some wars in some certain areas in the world, or a new oil field would be like, for example, discovered in a certain country that would affect the whole dynamic of operations that might need to do that. And these kind of uncertainties, they really affect how we plan and operate our power systems, as we will see in this shortly. But also there is the more of the short time forecasting, which is what would the load exactly look like tomorrow, or approximately look like tomorrow? What is the expected solar and wind generation for the next day? And the short-term forecasting is what we will try to focus on today, and more specifically about the solar generation forecasting. So why do we need forecasting in power systems? Because and why do we need to minimize the uncertainty? So, for example, why do we need to say that the solar generation for tomorrow on hourly basis will be, for example, some certain numbers? Why do I need to know this in advance? Because basically in power systems, most of the decisions we need to do are made actually in advance. So, for example, generators are inflexible. And what do we mean by that? If you want to turn on or to ramp up a coal-based plant, or a natural gas plant, you would need to hours for that action to actually be applied. So you cannot just, it's not a knob that you would increase and it would increase the next minute. Also, this becomes more difficult with the nuclear energy as well. So I think it does need around 1 day, from hours to 2 days, to actually ramp up or to turn off and to turn it off, to ramp up and down, or to actually turn the whole plant on or off. Also there is some, sorry. Also, there is some dependencies in or path dependencies in our operations and in power systems as well. So, for example, if I need to make a decision that I will operate this battery at this time of the day, I need to I need also to know that this battery will not be the state of charge of this battery will not be, for example, as 100% maybe in the night when it is most needed. So all of these actually does make the power system operators, they need to know in advance, or they need to have some kind of forecasting. And solar forecasting and wind forecasting are more typically more important, because solar and wind is not a dispatchable generation. You can curtail it, and optimally you want to avoid that. But more specifically, it would be very good to know how much solar and wind I would have at day X or at time X tomorrow, to actually uh, start planning around that with the other plants and generators. So I have mentioned the word tomorrow more than one time, because in the power system planning, at least, or one of the main power system planning components, or time resolution, let's say, is the day ahead market, which means or the day ahead operations in general. Usually what happens in the market is that the utilities or the generators, they submit their bids, what generators they are going to operate for the next 24 hours. And they do that based actually on the forecasted load, and they do that also based on the forecasted solar generation and wind generation needed for this the forecasted solar generation and wind generation that you would need. So they would actually plan the other generators on that. And this goes back to all what we mentioned. Minimizing uncertainty makes our plans, our all decisions better, less risky, and more cost effective on that. And so let's have a brief introduction about like some of the attributes of forecasting, which is time series forecasting is the process of predicting a set of values in the future based on learned patterns from historical observations. And to have an idea about the attributes of forecasting, there is a lot of attributes that goes into forecasting, but the most important ones are the lead time or the horizon and the resolution. The lead time or the horizon, which is basically how much ahead are you forecasting. And this could vary a lot. For example, for the day ahead market, we usually do a 1 day ahead, which is with a resolution of 1 hour, would be 24-hour set of values, one value for each hour. And for example, there's a lot of for the real time market. There's the intraday forecasting, which are basically could happen on 4 hours or 6 hours ahead as well. And this is what is known as the horizon or the lead time. And there is the resolution. The resolution usually is the time steps that you take for these forecasting. For example, based on the end goal for the forecasting application, you would need different time resolutions. For example, sometimes in solar generation they do 1 minute or even 5 minute forecasts, because or the resolution, sorry, is 1 minute or 5 minute, because it does drastically sometimes it change in 1 minute when a cloud covers for that. And if you are depending on an uninterrupted power supply for that, you might need to know that. But solar forecasting is usually done on hourly basis. And for that, these are the attributes, mainly the attributes of forecasting that I would say. That, and I've mentioned this more specifically because machine learning, the application of machine learning, which we will get into, is kind of adding a new attributes that would make the forecasting more useful, as we will see in upcoming slides. So let's see how important actually forecasting is. Like when forecasts go wrong, what could happen? We know the Texas instance that happened, which the actual load was, it did not happen because the forecasts were inaccurate. Because before the incidents, forecasts were there is also it's important to know that there is also some error, room for error in the forecast, and we do also design that we have a forecast error. But as you can see after the incident, which happened because a lot of the outages because of a lot of homes and places lost their electricity, so the actual load became far less than the forecasted based on the day ahead for that. And because the planning was done based on the forecasted load, a lot of there were like a lot of consequences for that. For example, if you have a generation you're planning as 100 megawatt for a load that is 50 megawatt, this could actually, as we all know, could have really terrible consequences on the whole operation of the grid, its stability and dynamics, which might unfortunately sometimes end up in complete blackouts. So that is what would happen if forecasts are typically wrong. And there is multiple studies. One of the most famous ones is what is the one study that was published around, still very relevant, and the methodology in that is very relevant, is what is the value of the day ahead solar power forecasting, and how does it affect the whole like our whole decisions in either production cost modeling or capacity expansion within the power system. So so this study discusses the value, tries to run multiple scenarios to study the value of day ahead solar power forecasting, and how improving forecasting could improve, or actually not only improve the operation, actually makes everything cheaper in our decisions. So the research question is, what is the value of solar forecasting improvements to the grid? And their approach in this study, which I encourage you to read, is comparing scenarios using forecasts with different accuracy. And you have the baseline forecast, which is, and then an improved forecast of 25%, 5%, 75%, and then 100%. And for each of these improved forecasts, there also was different solar penetration profiles, which is 4.5 or 9% or 13.5 and 18% solar energy by the annual energy percentage of solar. And also it was run on 2006 data on 1 year as production cost modeling study. And this is one of the main, the good insights, that how the impact of solar power forecasting improvement did end up happening on how much we are actually curtailing some of the solar power. So for example, in the forecast improvement, and in this column, you have how much the forecast improvement, and in solar penetration percentage in here. So when we just improved the performance by 25% on 9% solar generation, when compared to the baseline, we decreased the amount of solar power that was curtailed by 2.3%. And this happens almost constantly, actually always consistently, that whenever we, regardless of the amount of solar penetration and regardless of the improvement, it does always end up in less solar power curtailed, and therefore we're utilizing more the solar energy that we are actually installing, instead of ending up not using that. And we could see that for example, 100% improvement also is projected 9%, regardless of the solar penetration, and almost significant. 5% energy, for example, from a 100 megawatt solar farm is 5 megawatts, which is not something like something, let's say, you would not rather lose, or you would rather utilize. And it's more, you might also notice that the less the solar penetration, the more the less, or the more we are saving on curtailment. And this is because it does play, like the solar does play less role in that product, in that scenario. So it does end up happening like less curtail. And this is, for example, an illustration of 1 week of production. One day of production cost modeling with different forecast improvements. And you can see this is the baseline, and this is the 50% case of improvement. And in both the day ahead and the real-time market, we could see that that the generation completely is different, and how much solar we are actually using, and how much solar this is for the over forecasting, so how much biomass we're actually using. And it does end up affecting all of the other decisions for our most of other plants, especially the plants that we use as peakers and not as baseload, like in nuclear. So, for example, if you can see here, when we improve the forecasting, the gas combined cycle has a completely different behavior than that. And this also attributes on the cost as well, because the cost of ramping up and ramping down is also usually taken into consideration when planning for the most cost-effective way for the operation of a power system. And the cost of under forecasting are usually more drastic, because as you can see that when we actually improve the forecasts, we had less and less solar curtailment with that, which is a good scenario. Now, also just to finalize our discussion about the effects of how important forecasting is, we could see that the solar also, that it has a financial implications on that. So if we could see the solar power forecast improvements on the different level of solar penetration, it did save us in the best case scenario, where we had 100% solar improvement and 18% solar penetration. The annual generation cost savings are 30 million a year, which is not something to joke about. And if we normalize it as well, per unit of solar power generation, we are saving around 1.5 to 1.4 per megawatt hour, which is as well not something to ignore. And even in the worst case, or not the worst case, like the 4.5 solar penetration level with only 25% improvement in forecasting, we did end up saving quite not a negligible amount of money with that. So let's dig more into the algorithms for forecasting. So there are multiple approaches for that, and it has been a well-studied, well-explored, and well-studied topic for years, actually for decades. And there's a lot of ways that we could usually do forecasting, either directly or indirectly for solar, for solar power generation, to be more specific. So the most, I would say, popular, the most maybe used methods over the decades was the numerical weather predictions, which use physics equations actually to simulate the atmosphere. It is far more complicated than that, but it is computationally very, very expensive, and usually it does not take the grid, like it is not very effective in localizing on very small locations or very accurate location. It does depend on. It is good, for example, for forecasting for Boulder in general, but it's hard to tell it like to have a more accurate forecasting, for example, for the 30th or the baseline road in Boulder, or somewhere in the baseline road. So that is one of the main. So it becomes sometimes might be a little bit ineffective for solar farms power forecasting. And to add also, it is computationally very, very expensive. So it's hard to run it more than once a day or more than a few times a day. So it becomes hard to do it for intraday forecast or something like this. The other approach, which is a popular one, is also the statistical methods. Statistical methods are different from how numerical weather predictions. Numerical weather predictions use physics equations, basically, or approximated physical equations to know the weather, and from that we model how much solar power generation we need. The statistical model do not depend on any physical understanding, or most of them, let's say, do not depend on any physical understanding of the building of the whole governing equation, let's say. And what they do is they learn from historical patterns and historical data. And based on, they build probabilistic or statistical rules for that, that they try to, that these algorithms try to forecast the future ahead for that. So for example, if let's say we have a data for the last 10 years for how much solar power generation this farm or this solar plant is generating. We could use these statistical models to build some kind of to build a probability distribution or a deterministic one for how much electricity for how much this solar generation will actually do for this day, given that this day might be like June 10th, for example, or something like this, and given that the weather is X, Y, and Z. So they just build the statistical rules to build the forecasting for that. They are computationally very cheap, especially when compared to numerical weather prediction. You can basically run them thousands of times a day, I would say. And however, they lack they have a lack of physical understandings. And for example, they have no mechanism in ensuring that they will not predict solar generation, that there will be some solar generation at 11 p.m., for example. And they often struggle to generalize across multivariate inputs. And by multivariate inputs, we mean that usually most of these statistical methods take univariate inputs, which is the time. So they try to predict based on historical data, given the time. So they do ask like, what would be, imagine that I would, and why this matters as a multivariate inputs. Imagine if I ask you the following question to forecast. And I would say, can you tell me what is your prediction for the weather tomorrow at 12, which is July 11th at noon? A fair input would be, yeah, for example, 90 degrees. But for example, if I give you, yeah, but given that at 11 or yesterday or that there is another feature or attribute that says that there is a predicted a cloud coverage at that time, you would probably change your prediction maybe to 82 or 85 or something like this. Maybe this is not a very accurate example, but this is how multivariate inputs would help shape better predictions in that. And that is why machine learning might be a good idea. And let's a little bit have a why machine learning is a good solution in general, and why. I know it's a big buzzword, and maybe it's probably it's taking more hype than it should. But why you are seeing the machine learning applications everywhere? And that is because machine learning, and more specifically deep learning, follows the universal, what they call the universal approximation theorem, which says that the relationship between any input and output could be accurately approximated using neural networks. And what do we mean by that? I want to go to this visualization that I like. Did my screen change?
Yeah, you may have to like switch your
Yeah.
screen to the web page.
Okay, perfect. So this is one of the
No,
examples that.
it's not currently showing, so you may have to switch your screen
Okay,
because
sorry.
we're still looking at your presentation slides.
Sorry. So this is like a simple example for neural networks and how they are like just a visualization to why they are very effective in so many domains and fields. For example, you see them in computer, what they call computer vision, or like processing images. At the same time, there is an application for self-driving cars. You have the large language models and ChatGPT and their families and all of that, and also while being applied to forecasting as well. So, and as we mentioned that they follow the universal approximation theorem. So they could basically, if we want to visualize that this is a space that we need to classify, or we need to build boundary points between the yellow points and the blue points, and we want to build a classifier for that. And for this, we're going to build a very simple neural network and try to train this based on it. So as you can see, we have a simple 2 layers network for that, and it could not approximate the function very well so far. However, for example, if we increase the complication, it becomes as the equivalent of having like more features or more features in an equation. So for example, if we include more complications in this, or let's say more variables in this, it can build a classifier or a boundary that is far more effective. And that is why there is you are seeing machine learning just basically everywhere. And I would happy to talk to about this as as long as I can, but let's go back to the presentation itself. And this was just a visualization to why you're seeing machine learning everywhere and why it could be effective in what we're doing. So, sorry. And why now is the correct time? As you know, machine learning depends on having abundance of data. And recently, or now, we have relatively more data than ever, let's say. And we have also the availability of computation that was not really available 10 or 15 years ago, or actually even 5 years ago. So we have the availability of computation to run, to generate these like data sets and historical data and run and train these models, with the addition of the recent development in deep learning, transformer models, and foundation models as well. And we could use these developments to have better forecasting and generally therefore better operations for the power systems, and hopefully more and more solar penetration, or more and more solar penetration into our grid. So just a quick machine learning terminology before we dig into that. Let's say, what do we mean by training and testing data? Training data is the data that we use as historical observation to train our models. And the testing data is to evaluate our models, which are basically present in most statistical approaches to train anything. What are transformers? They're not the electric transformers here, or not, we don't mean by them the electric transformers. We mean by them is the architecture that was developed and is currently based, is the backbone and the main architecture behind, I would say, 90% of the models that we use on daily basis. For example, GPT, ChatGPT, or their families like Gemini or large language or any large language model, as well as the transformers that basically self-driving cars and are also based on transformers for that, and they are being still applied to some power systems applications. So, and what are foundation models? Foundation models and forecast and transformers could mean the same. But foundation model, a foundation model could use actually transformer as an architecture. But what we mean by foundation model is that there is one model that you could use it for multiple usages, which GPT is one example of that. You could use it to summarize a paragraph. You could use it to help you write something, or like generate synonyms for a word or something like that. Next token production is maybe not very relevant for our application. So why transformer models are effective, and why the solar, let's say the solar community think they should be explored at least. So as we mentioned before, that we have the resolution. I think we have we have both the resolution and the look ahead. We have the resolution and the look ahead attributes of forecasting. However, there is something that transformers do that the statistical models they do not, and that they actually generate the whole sequence in with the whole point in mind. What I mean by that is, for example, a statistical method, when they generate 24-hour prediction for the day ahead solar generation, they generate that point by point. However, transformer models do not do that. They generate the whole sequence. So when they generate the 1 p.m. prediction, they kind of also have, they see the whole sequence that at 8 p.m. it's also predicting like this, and at 7 p.m. it predicts like this. And this is generally is very important in forecasting, that seeing the whole sequence, and it has been proven to be a better method for forecasting in general. And maybe I'm not sure if you've heard of like attention, which is like they have also focus attention. So for example, they can have better mappers to the historical values and what they actually affect for predicting the future. And they also have, they can handle longer patterns. So for example, they might be very effective at maybe forecasting 48 hours ahead, or or 2 days ahead, for example, for that. And fourth is the flexible input, which is, in my opinion, one of the most effective or important ways for that, one of the most effective method that transformers or deep learning could do, which is it works well with multiple variables and different types of data. So what actually it could be that instead of only taking the historical data, in the example of statistical model, it could take the location data, historical data, satellite images, and weather data all into consideration when generating predictions. And that is, in my opinion, what makes them very effective for that. And we all could relate to that, as also when we think about it, that if I have if I want to predict something, the more information I have about this, I could predict it better and better for that. And finally, the ability to generalize and the ability to look back. So the ability to, what do we mean by the ability to generalize? Is that sometimes we might not have data to build the statistical models for the locations we need. So for example, if you want to build a solar farm in location X and you don't have historical data for the irradiance, it will be hard to accurately estimate how much data, like the solar generation that this new solar farm that you don't have any data on could could actually generate. But with the concept of foundation models that is being introduced, we have a better way to generalize across unseen locations that have no too few data, and this is one of the main research areas or research directions that are currently being addressed to do that. And finally, the ability to look back. The ability to look back while predicting is a very important feature, in my opinion, that helps a lot in predicting. So, for example, when you predict something based on historical data is different than the ability to look back. So, the ability to look back is what would be the weather in an hour, given that the last 2 hours it was like this. It was, for example, 100 or a 90. You would have a better prediction than just asking what would be the prediction, the weather in the next hour. And we said that. So there are some studies about how solar irradiance forecasting using temporal fusion transformer, which is one of the transformer models, and it has very effectively made forecasting better. So for example, in this, I wanted to show you, this is the method proposed in the paper in this, that as you can see, it has the number of used features is very rich in here. Therefore, it could actually have a better prediction for that. So for example, instead of taking instead of statistical models taking, for example, only the time, the use feature which are affecting actually the solar forecasting hourly is, for example, the diffused normal irradiance, the diffused horizontal irradiance, the wind direction, wind speed, and so on. So it does generate weather prediction, as you could see in the results of the papers and the experimental validation on that. And one of the interesting things and finding in the paper that the window size, which is the horizon of prediction, the more that you increase this horizon, the more that the transformer-based models are far ahead statistical models. And that is one of the most interesting things. And hopefully when being deployed to production, it will actually have a more effective method results or forecasting. And there is also another studies that were short-term prediction of solar irradiance without any data on that, locations. And I found this paper interesting for two specific reasons, which is that this is because they actually used multiple sources of features, and they included both images and actual numbers to actually provide train this model. And the other impressive thing, which is that they have tested it on locations that were actually unseen in the training dataset, which is a very important finding, in my opinion. That, for example, this is just some results on the model and on the location it was trained on, and on the location it was tested on. And you could see that, of course, and the tested on if the test and the train is from the same location, it will provide more accurate predictions than unseen locations. However, still this accuracy for an unseen without any data, or this amount, this error percentage without any training data is almost unheard of before foundation models. And this could give us the ability to build, for example, more solar on residential areas where we don't technically have historical data to build good estimates. And this is one of the findings in a paper that was published, I think, last month only. And however, there is still a big debate. Some people do not like transformers for time series forecasting in general, and some people like them very much. and they're investing literally millions and billions of dollars. There's Google have open source models. IBM have open source models that everyone can actually train and use for free. And this is, but there is also other teams that think transformers are very overrated for time series forecasting. And in my opinion, time will tell for that. And love to hear your questions.
Yeah, thank you, Muhy, for the presentation. That was a long talk. Yeah, quite packed with a lot of information. Uh, yeah, we've got a few comments on the Q&A box. Let's see. I think Frank asked what level of this type of large language models are the RTOs using now? Well, I'm not sure if any RTO is using LLM now, but do you have any insight on that?
Uh, I don't think the large language models in specific are text-based models. So if they're using it for something, they would be like for reporting assistance or something like this. For example, in the medical domain, they found that they could actually use a lot of AI large language models for this effectively. So I would imagine if large language models more specifically, these are only text-based, or they could process some images, but they are for reporting assistance or something like this.
Okay, I don't know for sure that some startups are looking at solar forecasting as a service. I think Clean Power Tech is doing something related to that, but I'm not sure if they're using large language models for that. But I don't know if we have a lot of startups that are like providing that service for solar forecasting for anyone operating solar farms or solar PV utility plants, that kind of stuff. Um, let's see. Is another question in here? What level of machine learning for forecasting are they using now? I think Kali just
Um,
asked that.
that is a good question, very good question. I'm sure. I don't. The problem is for utilities and third-party like third-party providers of forecast. They do not exactly tell you uh, like what the methods they're using, because it's mostly their like intellectual property or something like this. However, there was an anonymous survey that asked around 100 experts from different utilities in Europe and the US, and around 40% answered that they use machine learning for forecasting. So that is the best I know, to be honest.
Oh, okay. That makes sense. I mean, I would
I had a
reckon they probably still using statistical models or something like that.
I had a question I put in the chat, and
Okay, yeah, I mean, you can just
basically
ask.
it revolves around ISO New England's use of some model that they've developed internally to predict behind the meter solar so that they can properly set up their other fossil systems. And I was curious if you knew about that, whether you know whether other various ISOs are doing that, and what models they are using. Some of the problems I see are that they sometimes show solar overnight. They sometimes show production that's greater than they expect the seasonal capability would be. And generally, I don't have a lot of confidence in ISO New England's ability to do this job well, certainly not at the level that you're doing. Maybe you could sell your services to some of them?
Well, we can talk with them about like the ISO in New England. And in my opinion, I do not think they're using any statistical or machine learning based methods. That is my guess. And the inaccuracy in their like behind the meter maybe stems from the fact that they might be using numerical weather predictions, which are extremely hard to localize. And maybe they're using a hybrid approaches between that and that. But I do not think ISO and or as far as I know, they have like they said what the models are using, and or they have not really published a paper about that.
Yeah, they're
And
very non-transparent and
yeah,
holding all the info close to their chest because it's really annoying, as they say. They have trouble predicting their own front of the meter systems equally badly. But the thing that really gets to me is we have these methods out there where we can predict the future for the next hour, the next 4 hours, the next 24 fairly accurately these days. And you pointed out at the beginning of your talk how important it is to do that so that we don't have unnecessary curtailment.
yeah.
And I just find that the utilities approaches to this are so Neanderthal that it's going to be a problem. The bottom line is they never pay us for providing power that reduces the peak and delays the peak. And we got to get them to do that.
I completely agree with that. And when it comes to like changing power system is a rigid field, and unfortunately, and the grid is changing far faster than they're adapting. And one of the examples you've mentioned is that they're using like residential PVs, but they're not using it very effectively because just the field is changing farther than they're adapting to it, and that's a little bit unfortunate, especially
Yeah,
that there is in the literature.
one of the things
Sorry.
that happens that's really annoying is that somehow or another ISO New England is exporting some 100 to megawatts to over a gigawatt of power to other regions at the same time that it's importing from various places. And meanwhile, solar gets left second shift. I'm trying to figure out why we're running fossil plants in New England when there's solar available. And it's really kind of annoying that that's going on. But they
Yeah.
do have this neat model of how many tons per minute of CO2 we are putting into the atmosphere, which typically runs between 90 and 150 tons. Worst, of course, on clear winter days and on hot summer days.
Well, yeah, you've touched on a very good topic because, like, also not only like there is cost effectiveness, of course, and politics also plays a role in that, which sometimes might be out of the hand of like ISOs or.
And I think like regional operators on their own, they tend to be more conservative with adopting new technology because of risk and stuff. So they're like very conservative. They don't really evolve as fast as you would want them to be with the pace at which the grid is changing. Yeah, that's a real thing. They tend to be very conservative with their tools and their methods and all of that. But yeah, those are good points. We've got some couple of more questions in here that I think we can just cover before time runs out. I think Frank just asked, can this be used to help a new homeowner who wants to be off the grid in a net zero energy home, upsize PV or site battery and EV battery capabilities?
That is a good question, and yes, and there is actually research on how to use these models for household electricity production. So the answer is yes.
Okay. I think this is another question on solar insolation forecasting software for any local area globally with a Google Earth type technology on smartphones. I don't know if that's a thing yet, but it could be.
I'm not sure. I in my bet that Google Earth might be taking solar measurements, satellite-based measurements, which are different from sensors on the ground. And sensors on the ground are far more accurate than that.
Okay. We have about 1 minute left. I don't think we can take any more questions, so I'm just gonna wrap this up. Thank you, Muhy, for the presentation. That was a lot to unpack, and the recording for this will be online. Ella will be sharing more details on that soon. And I will just wrap up by saying that we've got the conference in Boulder next month, August, and I'm gonna be there. The division is gonna be well represented. So if you guys are gonna be coming, that'll be great. I would love to see you all. On Tuesday, I think August 5th, there's a poster session on technology research and applications that would include work on solar resource modeling. That's something I'm looking forward to. And then on Wednesday, um, that's August 6th. There's an oral session on grid integration, followed by a system symposium. Those are the relevant sessions that I think that are like applicable to resource applications. But anyway, I'll be there. I hope you guys will be there. I hope to see you all then. And thank you all for joining this session. And yeah, have a good rest of your day. Thank you all.
Thank you. Thanks so much, everyone. Bye.